This is the motivation for a memory consistency model, which is called release consistency. I'm sure just from the keyword release, some of you may have already formed a mental model of what I'm going to say. Basically, we're going to look at the structure of the program as follows: that the parallel program consists of several different parallel threads. P1 is one such. And if it wants to mess with some shared data structures, it is going to acquire a lock. We'll call it A1. And in the mind of the programmer, there is an association between this lock and the data structures governed by it. So long as they hold the lock, they can modify this data structure. And R1 is the release of this lock. So every critical section you can think of as composed of an acquire followed by data accesses governed by the lock and then a release. If the same lock is used by some other processor P2, and if the critical section of P1 preceded the critical section of P2, or in other words, P1's release operation, P1 R1, the release operation on P1 happened before. This must be familiar to you from our discussion of Lamport's logical clock. P1 R1 happens before P2 R2. That is the acquire operation that is being done by P2. If this acquire operation for the same block happened after the release by P1 R1, all that we have to ensure is that all the coherence actions prior to this release of the lock by P1 has to be complete before we allow P2 to acquire this lock, before we allow P2 to acquire the same lock L. That's the idea of release consistency. So we take the synchronization operations that are provided by the system, whether it is hardware or software, and we label them as either an acquire operation or a release operation. So it's very straightforward when you think about mutual exclusion lock. Acquiring the lock primitive is an acquire operation, and the unlock primitive is a release operation. So if there is a lock primitive and there is a preceding unlock primitive, so we have to ensure that all the coherence actions happen before I do the unlock, so that when this guy gets the lock and accesses the data that he's going to see are going to be data that is consistent with whatever modifications may have been made over here. That's the idea behind release consistent memory operation. Other synchronization operations can also be mapped to acquire and release. If you think about the barrier, arriving at a barrier is equivalent to an acquire, and leaving the barrier is equivalent to a release. So before leaving the barrier, we have to make sure that any changes that we made to shared data structures is reflected to all the other processes through the cache coherence mechanism. Then we can leave the barrier. So leaving the barrier is a release operation in the case of barrier synchronization. So what that means is that if I do a shared memory access within this critical section, and that shared memory access would normally result in some coherence actions on the interconnect, reaching to the other processes and so on, and if it is a SC memory model, you will block processor P1 until that particular memory access is complete with respect to all the processes in the shared memory machine. But if we use the release consistent memory model, we do not have to block P1 in order for coherence actions to be complete, to let the processor continue on with its computation. We only have to block the processor at a release point to make sure that any coherence actions that may have been initiated up until this point are all complete before we perform this release operation. That's the key point that I want you to get out of this release consistent memory model. So the release consistent memory model allows exploitation of computation on P1 with communication that may be happening through the coherence mechanism for completing the coherence actions corresponding to the memory accesses that we are making inside the critical section.